All right, we're doing assignment 38, and we're going to start with problem 30. So this has to do with rotational static. So static means two things. It can mean summation of force is 0 or summation of torque is 0. So since the problems we're looking at have an axis of rotation, that means that the summation of torque is 0. First, I'm just going to redraw the picture so we can conceptualize it. So first of all, here, this is the pivot point. Okay, so the pivot point is important because that's our axis of rotation. So when we sum torques, we're going to sum torques to this point. Okay, so first they show you here that there's a 4 kilogram mass. Now what's important is they show you the distance of this is 1 meter. And this is important because the force of weight of that object acts from the center of mass. So it's not going to act on this end or this end, it's going to act down like this. So that force is going to be mg. Now what's different about this problem, if you notice, is that the bar, the lever, actually this has a mass. Okay? So this, they tell you, is 6 kilograms, but where is this going to act? The weight is going to act from the center of mass, which would be here. Okay? So that's our other force. So it's also mg, the 6 kilograms. Here's our pivot point. They told us, and I didn't draw this to scale, and I apologize. This is 2. And then they have a ball like this. And they're not telling you the diameter of this because they're just telling you the distance of this from the center of mass is 1 meter. And then this weight of this mg is going to have another force acting down. So the first thing I want to do is I want to look at all the forces that are acting on this and where's the axis of rotation. The first thing I'm going to do is I'm going to draw my sign convention. So my sign convention is standard, we say our sign convention is counterclockwise is positive. Okay, so now I'm going to say summation of torque is 0 because it's going to be in static equilibrium. So all I'm going to do now is I'm going to add up all my forces times that distance of the axis of rotation. So let's start with the first one. So I have this 4 kilograms. The distance from this force to the axis of rotation is this distance here. So it's 2. But then it's half of this, so it's 2.5 meters. Now, in this particular case, because I'm solving for the mass, all of these are going to be mg times the distance of the axis of rotation. But just so I don't confuse you, I'm just going to go ahead and multiply times gravity. In this case, I actually wouldn't have to, but I don't want you to get confused because some problems are going to give you weight, some problems are going to give you mass. Okay? So this is going to be... The next thing I'm going to say is this, what's my sign, what is this, positive or negative? So here's my force, here's the axis of rotation, so it's going like this. So because it's going that way, that's counterclockwise, so that's going to be positive. So positive 4 kilograms times 9.8 meters per second squared times 2.5 meters. Okay? Now I'm going to look at this force. So this force is also going counterclockwise, so it's going to be positive. I mean, I should do this in a row, but because I do the picture, I'm just doing it here. So this force is going to be the mass of this, which is 6 kilograms, times 9.8 meters per second squared, times the distance from here to here to the axis of rotation, which is 1 meter. The last one is the mass of the sphere. Now this is going clockwise. So because it's going clockwise, that's going to be minus the mass, which I want to find, times 9.8 times 1 meter. So to simplify this now, I can just cancel 9.8 by everything. But the thing is, you have to be very careful on these problems because I've made mistakes where sometimes you have a weight and sometimes you have a mass. So you don't want to already multiply it times gravity if it's already in newtons. So when I do this, I'm going to get positive 10 plus 6 minus m. So 16 minus m, so remember it's equal to 0, so m is equal to 16 kilograms. So this is a simple problem because all my forces are already going perpendicular to the axis of rotation, so it's not so bad. All right, now we're going to look at number 32. So number 32 is a little bit more complicated. And when you look at the picture like this, you have a lot going on. The bar has a mass, which means that this is going to act from the center of mass, which is the same as this hanging mass. These two are acting from the same point, but then I have tension in this string here. So I'm actually going to do a couple of kind of diagrams before I start doing math, because back when I took statics, they taught us to draw all your forces going perpendicular to your axis of rotation, and then go ahead and before you start doing any math. Now, the first thing we need to do is we need to identify the axis of rotation. So even though this is in static equilibrium and it's not moving, what we want to say is, what if I cut this wire? Which way is this going to rotate? Well, this whole thing's going to what? Fall this way. Therefore, this is my axis of rotation. And that's going to be important when I start summing torque. So I want to identify where's my axis of rotation. So first I'm going to kind of draw the picture here of what's happening just to see what forces I have. So I have this hanging mass in the middle, M1, but the weight of this bar is going to act at the same place, so I'm just going to add it in the same place that I'm going to have big M there. Then on the end I have M2, and then I'm also going to have M3. And then I have going up this way my tension, and then they give me this theta. So before I start adding everything, the tension is not going perpendicular. So what I will need to do is I need to find the vertical component of the tension. This is why understanding vectors and components and taking forces and breaking it up into components is essential, because that's basic stuff you need to know physics. So now I'm going to redraw my picture. So when I start summing torques, that's already set up. So I'm going to have, what I have here is I'm going to have M1, and then I'm also going to have big M. Down here, the force is, I'm going to have M2 and I'm going to have M3. And then up here, remember, if I took this and I broke this up into horizontal and vertical components, that's my tension. My components would look like this. So this component here is opposite the angle, so this is going to be T sine of theta. Now I'm set to do my math. Okay, I have all my forces. Now remember, these are masses, so these have to be multiplied times gravity. This tension is already a force, so that one's already multiplied times gravity. Okay, and that's why I want you to go ahead. Like in the first problem, we really didn't have to write the 9.8, but we did it so we wouldn't make a mistake. Because this one, if you don't do it, you would make a mistake. So we know at this point, this is our axis of rotation. So our axis of rotation is important because that's where we're going to sum our torques to this axis of rotation. So first of all, I'm going to write my sign convention. And I'm going to say that counterclockwise is positive. And I'm going to say summation of torque is equal to 0. So what I'm going to do is I'm just going to start here on the left and do each one individually. So 0 is equal to, so first we have our M1, or we'll start with the bar. The bar is 20 kilograms, so that's big M. So I have, now remember, here's my axis of rotation. So I'm going like this. And I'm going clockwise, so that's going to be negative. So I'm going to have negative 20 kilograms times 9.8 times 1 meter. Because this is the big M times that distance to the axis of rotation. Now I have M1, which is 3 kilograms. So I have minus 3 kilograms times 9.8 times this distance from the axis of rotation, which is also 1 meter. Now I'm going to move over to these two masses. So again, these are going this way. That's also, this is clockwise, so clockwise is negative. So I'm going to have negative 1 kilogram times 9.8 meters per second squared times 2 meters. And then I'm going to do M3. So M3 is also going clockwise, which is negative 2 kilograms times 9.8 meters per second squared times 2 meters. And then last, going up, is this vertical component of the tension. Well, that vertical component of the tension is going counterclockwise, which is positive. So this is going to be plus T sine of 30 degrees times 2 meters, and that's all equal to 0. Now I'm going to do the math. So the first one, so 0 is equal to minus 196, minus 29.4, minus 19.6, minus 39.2, plus T times 1 is equal to 0. So when I add all these up, T comes out to be 284.2 newtons. So again, with this one, when you first probably looked at that diagram, you probably said, wow, this problem looks really hard. But when you break it down and do it to this point where you do the math, it's actually not hard at all. And you just don't want to make mistakes with, like, is it a mass or is it a weight? So make sure you carefully look at it and say, okay, these four are masses in kilograms, so I have to multiply them times gravity. And then this one is already a force to tension, so I'm not multiplying that. Because those are the little types of mistakes that you can make when working a problem. The more you write down on paper, the less likely you are to make a mistake. And that's why I just did it step by step by step, so then we don't make a mistake. That's it.